Introduction to Organic Nucleophiles, Electrophiles, Polarizability, and the Efficiency of Leaving Groups. So the best way I can think to explain a nucleophile or an electrophile is to start with the definition of a Lewis base and a Lewis acid. So what is a Lewis base? Well, it's an electron pair donor. And what's a Lewis acid? Well, it's an electron pair acceptor, a perfect combination. So here's the generic acid-base reaction where B represents any base. It's written with a non-bonded pair of electrons. It may have one or several or no non-bonded electrons, and it's written with a negative charge, and it may or may not be negative, but that's the generic symbol for a base. And here's the generic symbol for an acid, hydrogen bonded to some non-metal. So what is the mechanism of Lewis acid-base reaction? Well, the base donates, it's an electron donor, it donates a pair of electrons to the hydrogen of the Lewis acid. Now hydrogen is monovalent, it's only can have electrons in its 1s orbital. Its 2s orbital is way too high in energy, and it already has a pair of electrons in its 1s orbital, so it can only have one bond. It's monovalent. If it's going to form a bond with the base, it's going to have to break its bond to the non-metal, which then becomes a leaving group, A-. Here is the same reaction, but now with a specific example. Hydroxide is a strong base. Its pKb is negative 1.74. And hydrogen chloride has a pKa of negative 7, a really strong acid. So what's the acid-base mechanism? Well, the base donates one of its 3 non-bonded pairs of electrons, makes no difference, they're all the same, to the hydrogen. Hydrogen is monovalent. It's going to have to break its bond to the chlorine, and chloride becomes the leaving group. Now, chloride is classified as a good leaving group. Good because it's non-basic. I mean, its pKb is plus 21. Compare that to the pKb of water, which is about 16. This is 10 to the 5 times less basic, and that makes it unreactive and very stable. When you draw this reaction mechanism, think about the movement of electrons, because that's what we're showing with the arrow. We're not saying that hydroxide comes over here and bumps into hydrogen. Remember, we got thousands, millions, zillions of these species in a solution bumping into each other. They're moving every different direction. The arrows do not show the movement of the species. They show the movement of the electron from the electron donor to the electron acceptor. You can think of it like a quarterback throwing a football, and this is the path the football takes from the passer to the receiver, from the donor to the acceptor. Alright, so Lewis bases include what? Well, some of them are strong bases like hydroxide, hydride, and amide. Some of them are moderately strong bases like ammonia, pKb 4.8, and cyanide. And some of them are weak bases. Some are very weak, like water, alcohol, and fluoride, pKb 10.8. Most Lewis bases contain atoms with non-bonded pairs of electrons, and they are from group 5a, 6a, or 7a. For example, ammonia, group 5a atom, has one non-bonded pair of electrons. Oxygen in water, the group 6a atom, has 2 non-bonded pairs of electrons. And fluoride, group 7a anion, has in fact 4 non-bonded pairs of electrons. Let's look at Lewis acids next. So what constitutes a Lewis acid? What are some examples? Well, strong acids. Now, there are 2 kinds of acids. There are protic acids, those that contain hydrogen. For example, hydrogen chloride, sulfuric acid, hydronium all contain hydrogen. They are protic acids. Some of them are moderate, like a carboxylic acid, such as acetic acid is an example, or hydrogen fluoride. pKa is 3.2, pKa typically around 5. And even weak acids, or very weak acids, like water and alcohol. Notice the same species are amphoteric. They can be either very weak bases or very weak acids. Then also we have what are called non-protic acids. These are acids that do not contain hydrogen, like Bf3, aluminum plus 3 ion, iron plus 3 ion. Well, why, for example, is Bf3 acidic? Well, to be a Lewis acid, it has to be an electron pair acceptor. So why would Bf3 want to accept electrons? Well, it's sp2 hybridized, and it has an empty 2pz orbital. Remember, it does not have a complete octet. It would be very happy to accept the pair of electrons to form a fourth bond and use the empty orbital to do so. What about, say, aluminum plus 3 ion? Well, if aluminum is missing 3 electrons, it has room for some electrons in it. In fact, its pKa is 5.0. That's pretty much almost as acidic as acetic acid. You may recall having dissolved an aluminum salt like aluminum sulfate in water, and the sulfate is completely neutral, but when you put the aluminum ion in water, it is distinctly acidic, releasing hydrogen ion from the water. And the hydroxide from the water is tied up with the aluminum cation. Other polyvalent metal cations like iron 3, titanium 4, tin 4, lead 4, name any one, here's iron 2, react in similar fashion, producing hydrogen ion in solution. So they are in fact non-protic acids. Okay, so we've talked about Lewis bases and Lewis acids. It's time to talk about nucleophiles and electrophiles. So what's a nucleophile? Well, turns out it's an electron pair donor, same as a Lewis base. And what's an electrophile? Well, it turns out it's the same as a Lewis acid. It's electron pair acceptor. Why would two different terms use the same definition? Well, it's because they're very, very similar, but there are differences which we will explain. So here first is the generic reaction of a nucleophile, an electron pair donor, reacting with an electrophile, an electron pair acceptor. Similar to the symbol for a generic base, the nucleophile shows a pair of non-bonded electrons and a negative charge. And similar to the base, the nucleophile does not have to have non-bonded pairs of electrons. It can be neutral or negative, but the generic symbol is written in this fashion. And the symbol for an electrophile shows a positive charge, but just like acids, it doesn't have to be positively charged. It can be neutral. This is the mechanism for a nucleophile reacting with an electrophile. The nucleophile is the electron pair donor, and the electrophile is the electron pair acceptor, the same as the base to acid reaction mechanism, producing a covalently bonded group here. So what constitutes a nucleophile? Well, there's actually two types. We have nucleophiles that are in fact bases. We would call them basic nucleophiles, like hydroxide, like hydride, like ammonia, like any of the bases you're familiar with. They're all electron donors. They're all nucleophiles. But in addition, there are also non-basic electron donors, non-basic nucleophiles, such as alkenes and alkynes, and these are completely non-basic, but yet they are electron donors. So nucleophiles donate loosely held electrons. These can be non-bonded electrons, as in the case of hydroxide or hydride or ammonia. They can be pi electrons, as in the case of alkenes and alkynes. And they can even be sigma electrons, as for example in a compound like this, an alkyl group magnesium bromide. This is called a Grignard reagent. You'll use it in later organic classes. The carbon in the alkyl group bonded to the magnesium shares a bond that is not ionic. The electronegativity of carbon is 2.5. The magnesium is 1.2. The difference is 1.3. That's not ionic, but it's very polar. In fact, it's almost ionic. And given magnesium's propensity or tendency to give away its electrons, this reagent will readily break this sigma bond, giving both electrons to the carbon, producing a very strongly basic nucleophilic carbanion and a magnesium cation. So we could picture it this way. Nucleophiles are electron donors. They could be basic nucleophiles, bases, or they could be non-basic electron donors. Similarly, let's look at some electrophiles. We can have electrophiles that are in fact acids. They are acidic electrophiles, like, for example, hydronium ion and sulfuric acid. But there are also electron acceptors, electrophiles, that are non-acidic, such as carbocations. They have an empty 2pz orbital. Or you'll see carbonyl groups in ketones, aldehydes, esters, amides, and the like other carbonyl compounds. We can think of electrophiles as being comprised of both acidic electron acceptors and non-acidic electron acceptors. So in what way is an alkene or an alkyne pi bond an electron donor? Well, here's an alkene. This is ethene or ethylene, and it has a relatively strong carbon-to-carbon sigma bond here, in which the pair of electrons is shared directly between the positively charged carbon nuclei, which means it's a strong bond. About 83 kcals per mole is what's listed. The pi bond is a pair of electrons that are shared above and below the sigma bond, not directly between the carbon nuclei, so not as strongly held, only about 60 kcals per mole. These pi electron clouds are loosely held and can be donated to electron acceptors, electrophiles. So by breaking a weaker pi bond and reforming a stronger sigma bond, a more stable molecule can form, which explains the propensity of an alkene or alkyne to be an electron donor, a nucleophile. In what way is a carbonyl group an electron acceptor? Well, here's a ketone that contains a carbonyl group, and it reacts with a nucleophile. So an electron acceptor in general must have an empty, low-energy orbital available to accept an electron pair. I mean, every atom has empty orbitals that are far from the nucleus, but that orbital must be close to the nucleus to hold the electrons. An example of such would be a carbocation. It's got an empty 2pz orbital. The other alternative is that the atom is able to break a bond, release a leaving group, and create an empty orbital. Now the carbon atom in carbonyls, it's electron deficient, it's delta plus, because oxygen is more electronegative than carbon. And so the nucleophile donates electrons to the carbonyl carbon. At the same time, this carbon already has a full octet around it, has no more room for electrons, but it will break its pi bond to oxygen, which is a weaker bond. Oxygen takes both electrons. So carbon has made room for the new pair of electrons. It can do it because it has this weaker pi bond, and oxygen is happy to accommodate the extra pair of electrons. In effect, carbon has made room for the pair of electrons being donated by the nucleophile. And our product then is no longer an sp2 hybridized carbon, but rather an sp3 carbon with a nucleophile bonded to it. Trends in nucleophilicity, that is, big word meaning strength of nucleophiles, and electrophilicity, the strength of electrophiles. Table below gives us some comparisons. Now, for nucleophiles with the same attacking atom, the anion is a better nucleophile than the neutral atom. Here's what I mean. For example, in group 6A we have oxygen. Oxide -2 would be a much better nucleophile than the hydroxide oxygen, which is -1, which would be a much better nucleophile than the oxygen in water, which is neutral. And in fact, the oxygen in hydronium is not a nucleophile at all. It cannot lose its second pair of electrons. In fact, hydronium ion is exclusively an electrophile. So for nucleophiles with the same attacking atom, oxygen in this case, the anion is a better nucleophile than the neutral atom. Here's another example. We have amide. The nitrogen has a -1 charge. That would be a much better nucleophile than ammonia, which is a neutral nucleophile. And ammonium cation wouldn't be a nucleophile at all. In fact, it's an electrophile because the nitrogen no longer has a non-bonded pair of electrons. for electrophiles in the same group, the cation is a better electrophile than the neutral atom. So, for example, consider and compare hydronium and water. Now, water can be both nucleophilic or it could be electrophilic. It would be a weak electron acceptor as an electrophile, whereas hydronium would be a strong electron acceptor because it's positively charged. It's the cation. The relative rate at which a nucleophile reacts to displace or substitute for a leaving group is called nucleophilicity, so it's rate related. Consider the following nucleophilic substitution reactions. Here we have methanol reacting with hydrogen iodide, producing methyl iodide and water. So in this reaction, iodide displaces water from methanol and produces methyl iodide. Compare, if you would, methanol again. This time you're reacting with hydrogen chloride. Chloride is the nucleophile, displacing the hydroxyl group and producing water and methyl chloride. Now it turns out that the first reaction is much faster than the second reaction because iodide in the first reaction is a much better nucleophile than chloride. You see the leaving group, water, is the same in both cases. And so the nucleophilicity, which really is the relative rate of acting as a nucleophile, is shown in the following table. So in this table we see various nucleophiles. Some are classed as very weak. Weak acids can be very weak electron donors. Weak and fair and good and very good. And then these are the relative rates of reaction. So if we consider alcohol with a relative rate of reaction of 1 as a nucleophile, an electron donor, water is about 100 times faster. Fluoride is about 500 times faster than alcohol as an electron donor. Ammonia is about 300,000 times faster than alcohol. Hydroxide is about 2 million times faster, and here's iodide, and that's about 100 million times faster. These are large differences. So let's look at some trends here. For nucleophiles with the same attacking atom, the anion is more basic and a better nucleophile than the neutral compound. I hope that sounds familiar because that's what we discussed on the previous page, but let's look at some examples here. So for example, we already mentioned how hydroxide and water have the same attacking atom, and hydroxide is a good nucleophile while water is only classed as fair. Another example here is ammonia is a fair nucleophile, but amide is a very good nucleophile because amide is the anion. Here's a third example I've listed here. I'm comparing a carboxylic acid and a carboxylate. So the carboxylate with a negative charge would be a much better nucleophile than the carboxylic acid would. So acetate would be better than acetic acid, for example. All right, second rule here. Nucleophilicity increases down each column of the periodic table as polarizability increases with size. I'll explain polarizability on the next slide. Let's just talk about size for now. So here's a group: fluoride, chloride, bromide, and iodide, the group 7A anions. And fluoride is a fair nucleophile, chloride is better, bromide is better still, it's good, and iodide is very good. So as you proceed down any of the groups in the periodic table, nucleophilicity increases with size. Within any given row of the periodic table, let's look at an example while I read this to understand it again. So within any given row, here's the second period, the second row, nucleophilicity decreases from left to right. So you see methide is more nucleophilic than amide, more nucleophilic than hydroxide, more nucleophilic than fluoride. As basicity decreases, so pKb is negative 41, pKb negative 21, pKb negative 1.74, and pKb 10.8. So the pKb is becoming larger, becoming weaker bases, and as expected, they'd be not as nucleophilic, not as good at donating electrons. And as well, the polarizability decreases because they're getting a little bit smaller, but I guess the main reason is that the central atom is increasing in electronegativity. Fluorine is much more electronegative than oxygen, in turn more electronegative than nitrogen, and hence an over carbon. Here's a similar process using neutral atoms. Ammonia is more nucleophilic than water, which is more nucleophilic than hydrogen fluoride. In fact, hydrogen fluoride would not even be considered a nucleophile. It would be an electrophile. But that's the trend. Left to right decreases across any period. So, nucleophiles may be anions or neutral. If you look through the group here, you see anions and neutral atoms, but never cations. They are basic or weakly acidic, but never strongly acidic. So these nucleophiles, many of them are strong bases, some are weak bases, some are neutral, and even some weak acids up here, but never strong acids. And just a simple but important rule to realize is that all strong bases are good nucleophiles. If it's a good electron donor, it's a good electron donor. The importance of polarizability in reactions. I made reference to polarizability before. Let's see if we can explain it here. So let's start with the familiar compound water. Water has a permanent dipole, which means that there is a delta positive hydrogen and a delta negative oxygen. You see this shared pair of electrons in the oxygen to hydrogen sigma bond, we know is not shared equally. It spends most of its time near the oxygen and only occasionally near the hydrogen. If we could visualize the movement of the electrons in this area, it would be like a distorted cloud where the pair of electrons spend most of their time near the oxygen, only occasionally coming to hydrogen, but mostly here. So that's a permanent dipole. Now some non-polar compounds that have no permanent dipoles are in fact polarized. That is, they form induced dipoles in the presence of polar compounds. We're going to consider bromine and fluorine in the presence of a polar compound, ethylene. So here's the structure of ethylene. It's got a double bond made of a sigma bond, overlap of carbon's sp2 hybridized orbitals directly between the nuclei of the carbon. That's the strong sigma bond. It also has a pi bond made by the overlap of the unhybridized 2pz orbitals of carbon above and below the sigma bond plane. And they would appear like this, one electron, if you will, circulating here and one here. So these clouds of electrons are electron rich, they're somewhat negative, they're loosely held. What would happen if we brought a nonpolar molecule like bromine close to this electron cloud? Now bromine is completely nonpolar. Each atom has the same electronegativity, so this shared pair of electrons will be shared equally, spending equal time around both bromine atoms. If we can visualize the electron cloud, it would be something like this, like a rugby ball. If we bring that nonpolar cloud of electrons towards ethylene, it becomes polarized. One end becomes delta plus, one becomes delta negative as the electrons flee away and stay around the bromine that's farther from this electron cloud. Why do they do that? Well, like charges repel. And furthermore, bromine can do that because this pair of electrons is in the fourth period. They're relatively far from the nucleus. They're loosely held, and so the cloud can be distorted. The term for this is polarizable. You could think of it almost like a teddy bear. You can squash it and shape it. Another term that we sometimes use besides polarizable, we say that bromine is soft. If you compare fluorine, it also has a shared pair of electrons that's being shared equally. What would happen if we bring fluorine near this electron cloud? Well, not very much happens. It really isn't polarized much at all. The electron cloud is undistorted. Why? Well, because remember this shared pair of electrons is in the second period and they're being held fairly tightly by this highly electronegative atom or atoms, and they're close to the nucleus. So we say that fluorine is not very polarizable. sometimes the word hard is used. You could liken it to a golf ball, which is hard, versus a teddy bear, which is soft or polarizable. So we've seen polarizability in some of the halogens. Let's look a little further and let's compare the polarizability trend in the halide series. So here's fluoride, chloride, bromide, and iodide. What I'm saying here is that the polarizability increases down the group, and the nucleophilicity therefore also increases down the group as chloride is bigger than fluoride, bromide is bigger than chloride, iodide is bigger and softer and more polarizable than bromide. And this actually goes against the trend in basicity. Whereas fluoride is the most basic halide, pKb 10.8, that's a weak base. Chloride is pKb plus 21, not basic at all. Bromide is even less basic, pKb plus 22, and iodide, pKb plus 23. So just looking at the pKbs, you would say, fluoride would be the strongest base. Well, it is the strongest base, but in substitution reactions in organic chemistry, you will see that iodide is actually the better electron donor, better than bromide, better than chloride, better than fluoride, even though it's the weakest base, simply because it's more polarizable. It's softer. Alright, so last concept here is efficiency of leaving groups. On the first slide, we looked at the reaction of hydroxide and hydrogen chloride and said that chloride ion is a good leaving group because it's non-basic. That means it's unreactive and stable. Let's go a little further with that. In general, groups that best stabilize a negative charge, chloride is stabilizing this negative charge, they are the best leaving groups. They are in fact the weakest bases, they are the most stable as anions, and they are therefore the best leaving groups. What are they? Anions of strong acids, conjugate bases of strong acids, like iodide. So here's hydrogen iodide. Its pKa is -9. That's a really strong acid. And one of the reasons it's a really strong acid is because the iodide that's formed is quite stable and unreactive. It is completely non-basic. Its pKb is 23. In the following table, the relative efficiency of leaving groups in a substitution reaction is shown. So here we have the pKb values in order of various bases. So we're going from more basic to less basic. And turns out that the best leaving groups are those that are least basic, most stable. So decreasing strength as a base means decreasing reactivity as a base. Increasing stability of bases means increasing unreactivity as bases. I'm just saying this as many ways as I can till it clicks for you. Increasing ability to act as a leaving group. If you think of this in a very general sense, a reaction that goes spontaneously forward is one that would produce stable unreactive species, whereas a reaction that's going to produce a reactive species would not be favorable. In order to, say, drive out hydroxide as a leaving group from a reaction, you would probably have to heat that reaction, reflux it for some time to force the hydroxide off. Hydroxide is not a good leaving group because it's a strong base, whereas iodide, bromide, chloride are good leaving groups because they're stable and unreactive when they leave. Well, let's just get a little practice putting this all together. Can you identify the numbered atoms as a nucleophile, electrophile, or neither, and explain your reason? So atom number 1 here is a hydrogen, part of this methyl group. What is that? Is it a nucleophile, electrophile, or neither? I'll go through these quickly. You can stop the video as you need to predict for yourself. Well, it turns out that this hydrogen is neither electrophilic nor nucleophilic. Why not? Well, the carbon-to-hydrogen bond is a sigma bond. It's strong, and it's a non-polar bond. So this hydrogen is neither electron-rich nor electron-deficient. Since the bond is strong and the one s orbital of hydrogen is full, it's got no more room for electrons, so it's not going to be an electron acceptor. It's not going to break this bond. And it has no non-bonded electrons or pi electrons to donate, so it's not nucleophilic either. Okay, how about number 2? This carbon in the methyl group. Turns out that it is neither electrophilic nor nucleophilic. Now, the carbon to hydrogen bonds, we've already discussed, they're strong sigma nonpolar bonds. The carbon to nitrogen bond is also a strong bond, although it is polar. This carbon does have some electron deficiency. But in order to accept a pair of electrons, it would have to break this bond and produce a very reactive amide species, which would be difficult to do. So it's really not very reactive as an electron acceptor, nor does it have any loosely held electrons. It has no pi electrons, no non-bonded electrons, so it's really not going to be an electron donor either. What about this nitrogen, atom number 3? Well, I'm hoping you said nucleophile, because organic amines are basic. Bases are nucleophiles. Nitrogen has a non-bonded electron pair that it can donate. How about this alkyne carbon, number 4? Well, it's a nucleophile. The pi electrons are loosely held. They're electron rich, and as I implied before, it could break a pi bond and form a stronger sigma bond by being an electron donor, and that's what it does. How about number 5? There's an alkene carbon. Same as the alkyne, it's a nucleophile. The pi electrons are loosely held. Number 6 is the carbonyl oxygen. Electrophile, nucleophile, or neither. Turns out it's a nucleophile. The oxygen is delta negative, and it can donate pi electrons from the bond or non-bonded electrons. Number 7, the carbonyl group carbon. Well, that will be electrophilic. The carbonyl carbon in this aldehyde is delta plus because the oxygen is more electronegative. And so it would like to have some more electrons. Now, carbon already has 8 electrons around it. It's got a full octet. So as it is, it can't accept anymore. However, it can break this weak carbon to oxygen pi bond, and oxygen would keep the electrons, and that would allow carbon to accept another pair of electrons. How about number 8, the carbon bonded to the bromine? Well, it turns out that is also electrophilic. So this bond is somewhat polar. Bromine is more electronegative than carbon, but even more importantly, I guess, is the fact that bromine is a good leaving group. So a nucleophile that hits this carbon can displace this good leaving group bromide, and that would make room in this carbon for a pair of electrons from a nucleophile. So in fact, this carbon is electrophilic. So that concludes an intro to some important foundational concepts in organic chemistry. These concepts may seem vague, but as you study various organic reaction mechanisms, they will become clearer and more meaningful to you. Indeed, it is difficult, if not impossible, to understand organic mechanisms without an appreciation of numerous simple bonding principles such as these. So you may want to try my Visual Basic executable identifying nucleophiles and electrophiles. It's a zipped file. You can download it from www.chemrat.com, unzip it, and practice. And hope that helps you. Keep up the good work.